Welcome to this explainer. Every single time you tap your phone, open a laptop, or boot up a gaming console, you're actually interacting with a phenomenally complex digital metropolis. And today, we're going to explore the invisible city manager running your device. We're breaking down the brilliant mechanics of the operating system, looking at the exact blueprints of how this software handles literally billions of instructions a second without you even noticing. Okay, let's dive right into this blueprint. We'll be moving through 6 major areas today. First, the ultimate system manager. Then, the CPU processing and threads. After that, we'll hit traffic control and deadlocks, followed by juggling memory and space. Finally, we'll wrap up by organizing files and disks and protecting the entire system. Let's get into it. Starting off with Section 1, the ultimate system manager. Before we look at the individual gears turning inside your device, we really need to establish the sheer magnitude of what this master manager actually does on a second-by-second basis. So what is an operating system exactly? Basically, it's the core system software that manages all of your computer's hardware and software while providing essential services directly to you, the user. The crucial takeaway here is that without an OS, your computer is just chaotic, raw hardware. It's the critical bridge transforming a dumb collection of silicon and metal into a highly coordinated, usable machine. I mean, just look at the sheer scale of its daily responsibilities. The OS is simultaneously juggling process management, memory management, file system management, device management, and security and protection. It's spinning all of these plates at once just so you can seamlessly watch a high-definition video while downloading a massive file in the background. And because the world is complex, operating systems have to adapt to vastly different real-world environments. You've got batch OS for processing huge volumes of data without human interaction, time-sharing OS for multiple concurrent users, distributed OS spanning multiple physical machines, network OS for servers, and real-time OS for critical systems where even a microsecond of delay could mean total failure. Moving right along to Section 2, the CPU, processing, and threads. Let's step onto the fast-paced factory floor of the CPU. This is where the actual physical work gets done. And we're going to see exactly how active programs, which are called processes, are handled. Think of a process as simply a program in execution. It physically moves through the system in stages. It starts as new, moves to a ready queue, gets upgraded to running, might be shifted to waiting if it needs a specific resource, and is finally terminated. And tracking this entire journey, that's the job of the PCB, or process control block. The PCB stores the process's unique process ID, its registers, its program counter, and scheduling info as it bounces back and forth between queues. To keep this factory totally efficient, the CPU scheduler steps in. It evaluates processes using specific algorithms, like first come, first served, shortest job first, priority scheduling, or round robin, to decide who actually works next. And it absolutely doesn't just guess. It relies on strict performance criteria, precisely measuring CPU utilization, throughput, waiting time, turnaround time, and response time. Now, what's really fascinating is that processes can be broken down into even smaller units called threads. A thread is literally the absolute smallest unit of CPU execution. We've got user threads and kernel threads, and the OS links them together using multi-threading models like many-to-one, one-to-one, or many-to-many. This is exactly what allows a single app to execute multiple complex tasks at the exact same time. All right, part 3, traffic control and deadlocks. Moving out of the processor, we step into the collision zone. With so many threads and processes zipping around, the OS has to actively prevent multiple programs from crashing into each other. Because if that coordination fails, you get a race condition. This happens when 2 or more processes try to grab the exact same shared data at the exact same time. Complete chaos, right? To prevent this and solve what's known as the critical section problem, the OS enforces 3 strict rules: mutual exclusion, progress, and bounded waiting. It does this using synchronization tools like semaphores, mutexes, and monitors. Think of them as high-speed traffic lights for your data. But wait, what happens when those traffic lights totally fail? Imagine massive gridlock where processes are just waiting for each other indefinitely. That is a deadlock. It's often mapped out mathematically on a resource allocation graph, which visually represents this gridlock and essentially forces the OS to intervene immediately. This is where our OS City Manager acts like an aggressive traffic cop. It uses 4 distinct methods to clear the jam: prevention, avoidance, detection, and recovery. Depending on just how severe the deadlock is, the OS calculates the best path forward to untangle the whole mess and get your frozen apps running normally again. That brings us to Section 4, Juggling Memory and Space. Next up, let's look at the active workspace. This is the memory management department, where the OS builds a dynamic spatial map for all of its data. Here, the OS relies on a really clever illusion. It seamlessly translates between two very different types of addresses. The CPU generates an imaginary map called the logical address, but the physical address is the actual hardware location inside your memory sticks. The OS manages this continuous, split-second translation through contiguous memory allocation, using single and multiple partitions, and by actively swapping processes back and forth between your ultra-fast RAM and your much slower hard disk. This swapping magic relies on virtual memory and demand paging. Basically, chunks of memory, or pages, are only loaded exactly when you need them. But if a required page isn't there, you get a page fault. Now, a fault sounds like a bad thing, but it's totally normal. It just triggers the OS to seamlessly fetch the missing page from the disk and pop it into the physical memory. Of course, your physical memory fills up pretty fast. When the workspace is totally maxed out, the OS relies on clever page replacement algorithms to decide which old data gets evicted to make room for the new stuff. It might use first in, first out, least recently used, or an optimal algorithm. It is essentially playing a continuous, high-speed game of musical chairs with your data. Okay, Section 5, Organizing Files and Disks. We're descending into the deep physical archives now. This is the File System and Disk Management Department, where the OS organizes your permanent data so it doesn't just vanish into thin air when you turn off the power. At its core, a file is just a collection of related info. But to the OS, every single file has unique attributes: name, type, size, location, and protection. Files are accessed through sequential, direct, or indexed methods, and they're organized in single-level, two-level, or tree directory structures. Ultimately, the OS maps all of this physically onto the exact tracks, sectors, and cylinders of the actual disk hardware. To read those files quickly and without literally burning out the mechanical parts of your hardware, the OS meticulously schedules disk access. It uses algorithms like first come, first served, shortest seek time first, scan, and cscan to sequence the reading and writing. Grouping reads by location, for instance, keeps data retrieval blazingly fast while saving your physical hardware from totally unnecessary wear and tear. And finally, Section 6, Protecting the Entire System. We have reached the fortress walls, everyone. We've seen how the OS manages internal operations, but it also has to act as a perimeter defense, strictly controlling access to all system resources to protect against outside threats. Because make no mistake, it is a war zone out there. There are malicious invaders constantly trying to break into this bustling digital city we've been exploring. Viruses, worms, and Trojan horses are explicitly designed to exploit any tiny vulnerability, steal your data, or just outright crash the perfectly balanced system we've just spent time analyzing. But thankfully, our master conductor pushes back. It actively defends the city using some incredibly robust mechanisms. Through strict authentication to verify who is who, encryption to scramble data away from prying eyes, and firewalls to block unauthorized access, the OS ensures your digital life remains completely safe from outside interference. So from those high-level executive decisions all the way down to the tiny threads on the CPU factory floor, through the traffic grids, the memory swaps, disk structures, and firewall fortresses, the scale is truly staggering. The next time you seamlessly open an app, save a photo, or browse the web, just think about the incredible split-second coordination happening right under your fingertips to make it all possible. Can you even imagine the utter chaos if this invisible manager took a single second off? Keep wondering about the tech around you, and as always, keep learning.